Hello, in the last video we did the problems in this left column, and this one we're going to do the problems in this middle column. If you've not worked these yourself, I encourage you to pause the video, work out these 6 problems yourselves, and then come back and check them. The idea here is to first of all find out if these converge absolutely, converge conditionally, or diverge. And if they do converge, approximate the sum which is an infinite sum, by summing the first 50 terms. And if the test you use gives a bound on the sum or bound on the error, then go ahead and give me that as well. Be sure that you're showing that you have met all the conditions to use a particular test. Okay, so let's go down. We'll start with G. We're doing G through L. All right, so here's problem G. Cosine of k pi over k. Well, the cosine in k pi in the numerator is, since it's at natural numbers of multiples of pi, it actually turns out that's just alternating between 1 and -1, starting when -1 when k is 1. So in fact, this cosine of k pi is equivalent to saying -1 to the k. It's -1 when k is odd and +1 when k is even. The denominator, k, of course, is just a positive number. So what we're doing here is getting an alternating series, and that should have said starting at 1, not 0. If you start at 0, you're dividing by 0, so that's not good. So start that at 1. Okay, so this is an alternating series. In fact, it's just the alternating harmonic series. We've already worked out this one out. We know that it converges conditionally by the alternating series test. And so if we sum that from k equals 0 to infinity, it will converge to something, which we haven't worked out what it is. But if we do a um, sum from k equals, again, that should be at 1, say 1 to infinity. If we sum from 1 to 50, you get negative 0.68324 something. Okay, and since this is an alternating series, we can give us a bound on the size of the remainder, the error. So the remainder of 50 is absolute value is less than the absolute value of the 51st term, which is cosine of 51 pi, which is -1 over 51. To the absolute value, you get 1 over 51, or about 0.0196. So the error is less than that. So the 50th term is actually positive term. Positive term when k is even. So our estimate will be an overestimate. It'll be over the limit, and then it could go down by no more than this. So our actual is on the top side is about, I'm gonna round off to 3 decimal places, 0.683, and on the, or if we go up, round up, I should 683 is rounding up. 683, and we could go down from there. It's no higher than that. It's actually no higher than that, and then it could go down by as much as 0.0196 below this, or 0.020 below this. Which would be, yeah, 0.020 subtracted from that will give you the negative 0.703 negative. So this true sum is something between those two. So that one converged conditionally by the alternating series test. Okay, the next one. We have this nice little rational function here. And when you have a rational function, if you'll just look at what's happening with the leading terms here, if you just ignore the 2 and the 2k plus 1, you factor out a 5/3, and it looks like k over k squared or 1 over k. So this should probably diverge. So if it's if we could get the inequalities going the right way, we might be able to try a direct comparison test, but it's going to be easier to do a limit comparison test. The direction of these inequalities may not work out the right way, or it may be hard to show. So we're going to take this fraction here, divide it by 1 over k. Well, this turns out to be this, and we've done enough of these. We know this limit is going to be the limit of this, what's happening on the first part here, which is just 5/3. And so since that has a limit, that says that both series do the same thing. So the harmonic series we know diverges, the sum of 1 over k diverges. So this diverges as well to infinity. And of course it has positive terms on it. So that was all we needed for that. The next one, 7 over k, natural log of k to the fourth. First thing I would do is natural log of k to the fourth is just times 4 natural log of k. So this is 4k natural log of k in the denominator, 7 at the top. And so it looks like an integral test might be in order. Notice that it is a positive term series. Since natural logarithm is an increasing function, k is an increasing function, k times log of k is an increasing function. The denominator is increasing as k gets bigger, the top staying the same, so the whole fraction is getting smaller. So that's clearly a decreasing term. We could also find it's decreasing by looking at the derivative. Okay. So there's an undefined term when k is 1. We'd be dividing by 0. So it's important we avoid that term. But this sum starts at 5. So our integral in an integral test will start at 5 as well, because the sum starts at 5. So in any event, we have this. So our f of x is 7 over 4x log of x. Replace the k's by x's. Up here, k is a natural number, or, well, from 5 up, natural numbers. Here is a real number from 5 up for x. Bring the 7/4 out front. This is x log of x to negative 1. Do a derivative. So it's negative that x log of x to the negative 2. Then the derivative of the x log x, which is going to use the product rule. So first times derivative of the second plus second times derivative of the first. Derivative of the x is 1. Derivative of log x is 1 over x. So that becomes 1 plus log of x. We'll put that in the top with the, I don't know where the 7 disappeared to. Let's get that back in there. With the 7, and we got the 4, and here we have x log x squared in the denominator. I could have used the, pull the 7/4 out front and use the quotient rule as well. Would have gotten me the same place. Any event, we're at this point right here, and let's see what happens. Well, you got log of x times x, and then square it. That's definitely a positive number. You've got 1 plus log of x. That's going to be positive as long as x is to the right of 1, which it is. And so you got all this is positive, but then you got the minus in front. So that's going to be a negative thing, which means the derivative is negative, which means the function is decreasing. So there's at least 2 different ways you could argue that the function is decreasing. But you do have to make that argument before you can use the integral test. So the integral test, then I can integrate from 5 to infinity. Normally it's 1 to infinity, but since our sum started at 5, we're going to start our integral at 5 as well. So it's from wherever you start your sum up to infinity. All right, so anyway, this one we let u be the natural log of x. Du is 1 over x dx. So we've got the 1 over x there. We put with the dx. We've got 1 over log of x, and we've got the 7/4. Remember we pulled that 4 out using the property of logs. Property of both limits and integrals brings that all the way out front. So we're integrating from 5 to b, and then taking the limit as b goes to infinity. That's, of course, how we handle a improper integral with infinity there. All right, so anyway, this becomes u. All this right here becomes du. We're evaluating from x equals 5 to x equals b. So without switching these limits, I need to put x equals there. That's important. Otherwise, these would be u values. The other alternative is to switch them to be actually u values. I could let this be log of 5 and log of b. Would be okay too. But anyway, what I have for an antiderivative 1 over u is the logarithm of the absolute value of u. So that's the log of u. Normally you'd need absolute values on that, but log of u for 5 up is going to be positive for one thing. Okay, and then we evaluate from 5 to b. So that's log of b, that's natural logarithms, minus the natural log of 5. At this point, I should have gotten rid of that stuff there at the end. And now you take the limit as b goes to infinity. Well, log of b is going to approach infinity, and log of that's going to approach infinity. And this is a constant, so this whole thing is going to approach infinity. So it diverges by the integral test. All right, let's look at the next one. 5n squared plus 6n plus 1 over 4n squared plus 6, sum from n equals 1 to infinity. Notice, first of all, this is defined there. In fact, it's defined everywhere for any real number n, but certainly for all natural number n. And I'm going to claim that that diverges to infinity. And you could do it just by the divergence test here. If you take the limit as n goes to infinity, this thing approaches 5/4 or 1.25. It's not 0. So divergence test tells us that diverges. And of course, we know it diverges to infinity because we're just adding up infinitely many positive things. The next one, 5 to the k plus 2 over 2 to the k plus 3 to the k. All right, so I'm going to take the limit as k goes to infinity. And what I did is I multiplied the top and bottom by 1 over 3 to the k. All right, so this made this like this, and I'll distribute. So this is 2 over 3 to the k. This is 5/3 to the k. This is 2/3 to the k, and then this is just 1. Then I can take the limit of all 4 pieces. This part right here goes to 0. So the bottom goes to 1. This part goes to 0, but this part goes to infinity. So you get infinity over 1 or infinity for that. Definitely not 0, so that diverges by the divergence test. You could have also compared with the direct comparison or limit comparison to the harmonic series or to this series right here. I'm not sure about the harmonic series, but that's a P series, I should have said. So you can compare to that. But the divergence test works there. Okay, how about this one? The sum from k equals 2 to infinity of 3 to the k plus 2k plus 3 over 8 to the k minus 11. Let's see. I think I originally had k equals 1 actually there. And that's okay. The first term is negative when I have that. So that's, something positive in the top. And you have 8 minus 11 is negative 3. So it's negative 3 in the bottom, and I guess it's 3 plus 2 plus 3 more is 8. So negative 8/3 is the first term, but all the rest of the terms are positive. So once you get to k is 2, you got 64 minus 11 at the bottom. Everything at the top is clearly positive. So all the terms are positive except for the first one. And we'd like to compare it to 3/8 to the k. That should dominate over this other stuff. But this one's a little bigger than 3/8 to the k, which is going to be converging when you sum it. So direct comparison is not going to work. So we need the limit comparison. So we'll just limit comparison it to 3/8 to the k. All right, so this is going to be a 3 to the k. It's going to go in the bottom with this. And then, well, I'm going to actually think of this as a 1 over 3 to the k and a 1 over 8 to the k here, 8 to the k here. So see if that makes sense, that that's the right thing. So if you do this, we're multiplying by 8 to the k over 3 to the k, which is the same as flipping them again and putting them with like this as reciprocals. Okay, so anyway, that's legit. And then we distribute here, and that makes a 1 here, makes this 11 over 8 to the k. This makes 1. This is 2 to the k over 3 to the k, 2 times k over 3 to the k. And this is 3 over 3 to the k, which is 1 over 3 to the k minus 1. Now you take the limits. These ones are constants, so they're fixed. This one here is clearly going to 0. Top is constant, the bottom is going to infinity. Same way for this one here. This one's also going to 0. It's a little harder to see, but not too much. You just do L'Hopital's rule once, and you see that this is going to go to 0 as well. And then all that goes to 1. Well, 1 is a legitimate limit. So we get a both series do the same thing. Since the original is a convergent geometric series, a base 3/8 is between -1 and 1, then this one converges, and it converges absolutely because it was, if you take the absolute value of that first term, certainly that's going to still make it converge. And here we did summing it up from, I'm not sure what I did here. If I did summed up from 2 on or from 1 on. Let me just do it from 1 on. So let's fix that. Let's go back to 1 here and see what the sum is. So I can use this, for example, sum k equal, let's actually start at 1. Oops. 1 and go up to infinity. No, we're just going to go up 50. May not be able to do it going up to infinity. And this is, and then of course our directions were to approximate this by summing up the first 50 terms. And the denominator 8 to the k minus 11. All right, and so that's what I got there. Okay, so that's that, and oops. Let me try that again. There we go. All right, and so that's, yeah, that's what I have. So I did sum it from actually 1 to infinity. Well, 1 to 50. Okay, there we go. Okay, so there's that one. Okay. Okay, so that brings us to the end of the ones I wanted to do on this particular video. Now in the next video, let's pick this up and do these last 5 over here in this column. If you haven't done those yet, do those yourself before you come back for the next video. Bye-bye.